series of lectures and also thank you for the introduction. So for my series of the lectures, I will use my talk to give my introduction. So in my talk, I will give some introduction to 3D algebras. 3D algebras is a kind of algebra structures appearing in many fields. It has relations with many fields in the mathematics and the physics. As some of the French mathematicians point out, the 3D algebras deserve more attention than they have been given. In particular, at the end of the last century, 3D algebras have play an important role in the quantum field theory. The normalization of the theory given by the quantum parameter. So, because the history of studying the 3D has more than, I think, 50 years ago. So it's impossible for me to list every result and or mention every reference. I think I will give the talk the aim of my talk is I want to give explain why 3D algebra is so interesting. Since most of you are not the expert in the field, that's the beginners, so I will pay attention to explain the relationships between the 3D and some related structures. So that's my aim. So I will not give the more details about some results, just to try to explain why 3D appear here and why it's so important, why it's so useful. So I hope if you have any questions, please stop. Okay. Okay. So let's begin. So for any algebraic structures, at first I will introduce the first thing is I will introduce the definition. So I give the definition. The definition is very easy. So a 3D algebra is a big space with a binary operation dot, and this is satisfied some identity. So it's very easy. It's y, only one identity. So it's only this identity. This is called 3D. So I will explain this identity. So why is it called 3D? In fact, such algebra structures have many names. The first name is all of them are equivalent. The name appear in different fields. The first name is the left-centric algebra. Why? Why is it called the left-centric algebra? So if we denote the associator by xy z equals to x dot y minus. So if the oscillator is 0, the algebra is a associated algebra. But for this one, it's equivalent to this identity. Our associator is left-centric for so that means is the left-centric means is the third eta is equivalent to the if you change the first two variables x, y, z equals y, x, z. So here give the notion of the left-centric. So left-centric means the third eta is the left-centric in the first in the left two variables. This notion is given by Wimber from geometry around 1962 or 3. I think his paper published in Russia in the 1 year ago in the 1962, but we found the English translation by the American Mathematical Society in the 1963. He studied in the homogeneous. Okay. So this equals this one. Another equivalent, almost equivalent notion is this way gives the notion of the left-centric angle. We also can consider the right-centric angle. Right-centric angle is just the oscillator is x, y, z equals to x, z, y. Right. Okay. So that means the oscillator is equals to the if you change the right variable is the same. If for this one, if we denote equals to y, okay? Just define a product in the object algebra. You can see it's very easy. So A is left-centric. Equals to A dot is right-centric. So that means the study of the right-centric is totally parallel to the study of the left-centric. So usually for my talk, although in many reference we still use the right-centric notion, but we unified to use the left-centric because here that means the study the results is totally parallel. In fact, the 3D was the first given by the Harvard in the almost the same year. Okay. They gave the notion of the 3D by the right-centric. So in many references, we also use the right-centric to denote the 3D, but in order to be to be treated in a uniform way, we use the 3D to also use the left-centric to denote 3D. Okay. So why is also called 3D? Later I will give the more details to explain. It's related to the closely to the D angle, so we give more details. Now we just give the certain name is 3D. By the discovering the deformation theory of certain angles. Okay. The third name, the fourth name is given by Chengming form. It's called quasi-associative. Why is it called quasi? Because obviously the associative algebra is belong to a special pre-D. So in some things, the associative algebra means x, y, z equals to 0. So the pre-D can be regarded as a natural declaration of associative algebra. So it's given by Chengming. In the last lectures, in the study of the fifth base, he gave the notion. He used this notion to start to give to explain what is the nature of some important infinite dimensional algebra. So he used the notion to explain the nature of the Verso algebra. Another is also called Wimble algebra. Due to the Wimble, who is the first to give the notion of the pre-D of causal algebra. Causal algebra is also due to the geometry causal in the last 60 to explain. To find these structures is related to the affine structures in the group of affine manifold, also called causal Wimble. Both due to their finite work of the algebras, due to their finite work to the relation with the geometry. Okay, so we can see from they have the many names, several names. Both of the name, but up to my knowledge, up to now, the notion of pre-D and the vector symmetry, these two notions are most popular. From my introduction, we have seen in some things the notion of the vector symmetry algebra is very popular in the study related to the geometry, and the notion of pre-D is to the algebras. So also, I made such experience when I submit some papers to some geometric journal. The referee usually like the notion of the vector symmetry. But if I want to submit the papers to some algebra paper or the mathematical physics paper, they like to use the notion of pre-D. Sometimes some referee also suggest me to change the notions, although they are the same. So it's I couldn't say whether it's fair or unfair, but we must to be careful. Okay, so next I will explain why it's called pre-D. So they have the very important the relations to D algebras. Okay. So in fact, the pre-D have two fundamental. From the identity, we can imply two basic results. First, x, y equals, if we define the bracket minus imply, this imply the x, y So that means for any query, the commutator is reliable. So in these things, it's very natural to call such algebra structure is called query. Oh, sorry. Why? They have a very simple the proof. In fact, if algebra structure is called the commutator is a algebra, they have another name. It's called the EQuaLS8. In these things, the query is a special EQuaLS8 algebra. EQuaLS8, they have identity. So if the commutator is a algebra, it's called a EQuaLS8. They have the equivalent identity is x, y, z plus y, z, x plus 3xy equals to y and z. If algebra structure satisfies this condition, it's called a limito, and it is equivalent to the commutator with the algebra. So in these things, this gives the equivalent to the commutator satisfy the Jacobi identity. From this slide, we can see this result is very natural because the sum of three terms is equal, but for the query, every pair is equal. So in this instance, it's special EQuaLS8. Very special EQuaLS8. Whether every EQuaLS8 is a query, the answer is no, because only for the query, only the commutator is the algebra is not enough. They have another property. This imply this one, but the converse is not right. So we should know what is the equivalent condition for this identity. It's another identity. Another property. So first, the commutator is a algebra. Another property is very important. If we define for query, the left multiplication operator define xy equals to x equals to y, is 1, and rx y equals to yx. Then R is we denote is a linear map from A to GLA. The linear transformation of A. Okay? And this condition implies R A is a representation of A right. Okay? That means for a given query, the left multiplication operator defines a representation of the commutator algebra. We can see this one is just the x, y, R, S, L, Y equals R, X, Y. So this is R, X, this R, X, Y minus R, X, R, Y equals R, Y, X minus R, Y, R, X. Okay? So because x, y minus y, x is the bracket, so we can solve this one. This property is very, very important because there are several reasons. So when we studied, I think most of you should know something about the Lie algebra. Okay. So the Lie algebra, one of the important the role of Lie algebra is the representation theory. But unfortunately, usually we only know the representation theory just by some for example, the simple Lie algebra we have the highest weight or some character or something. But if one want to construct the representation equation, it's not easy, right? We only know some property of the representation, but if one want to construct some concrete representation, it's not easy. So the most natural way is to construct the representation is the adjoint representation. That means by the Lie algebra structure by themselves. So if Lie algebra acts on itself, the underlying vector space of the Lie algebra itself, we only know the adjoint representation. Here, it gives you another choice. If Lie algebra is the commutator of a pre-Lie, there will be two representations acting on the vector space of itself. One is still a adjoint representation. Another one is given by the left multiplication of the A, deduced from the pre-Lie algebra. Because the representation is decided by the structure, by the algebra structure of the pre-Lie, so we have the two choices, and it will be more ways to construct the representations. So this property is very important. Then that means we can transfer the constructing the representations to how to construct algebra structures. So in some sense, it's equivalent to transfer the representation to the algebra structures, also from the algebra structures transfer to the representations. So this property is quite important. In some sense, when we studied some interesting structures in the geometry, so we usually use these structures to give some construction of interesting structures in the double space. Later I will give you more details about how to use this property to give the more examples. Okay, from this one we can see the pre-Lie in some sense is quite close to the study of the Lie algebras. The commutator is Lie algebras, and the left multiplication operators to construct a representation of the commutator Lie algebra. Okay. So this is the fundamental. So in this sense, it's called the pre-Lie. It's very natural and very very natural. Okay. Of course, there are some sub-classes of the pre-Lie. The first is the social algebra. I think we need to say more about. Another is called the transitive. Or it's also called another name is complete. So it's a kind of the pre-Lie. So satisfy another additional condition. Is Rx is default for INAX. Okay, this class is very important in geometry. So Here it means the left multiplication operator is give a repetition, and the Rx is right multiplication is important for every x. This important is I will show you the pre connected to the fun connection. Here, why it's called complete. This property means the connection is complete in geometry. Complete means the joystick can extend to any interval. So it comes from the geometry. So anyway, and this property also play an important role in the study of the structural theory. Later we will see in some things such property, it's not transitive, but this gives some sign related to the radical of the fluid. Okay. Another subclass is called the left derivation. Really, or right derivation. It means the Rx is right. See, is a derivation of A right. Means left multiplication operator not only to give the representation of the combinatorial algebra, but also the left multiplication operator is a derivation of the combinatorial algebra. This property, this kind of the pretty also corresponding to some, to some important structures in geometry. In some things, this corresponding to the group to adapted to the structures related to the inner automorphism group of such structures. It's in geometry. Another one is called no-equal algebra. No-equal algebra is the pre plus Rx Ry equals to Ry Rx. So this pretty is left multiplication operator is repetition, and the right multiplication operator is commute. The two conditions. The two conditions is independent in some things, and this the algebra is also important in the vector physics. The first this structures was introduced by the Garfond and Dorfman in the study of the Hamiltonian operators. But unfortunately, of course, some persons called such structures they called the Garfond-Dorfman algebra. But later, it was restudied by the Neukov in the study of the bottom bracket of the Hamiltonian domain. So, but in the last 90s, the notion was given by the algebraist Osborne. I think he didn't know the inner work of the Garfond Dorfman. That's gave the notion by following the Neukov. Okay? So they also has the close relationship with the lattice algebra. So it's a very important subclass of the 3D. So this connected to the study of the infinite dimensional algebras and the lattice algebras and in metaphysics. 5. Bisymmetry. All associated symmetry. So this means why is it called bisymmetric algebra? We can give the left symmetric algebras as 3D, but we hope is x, y, z commutator equals to yxz. Also, at the same time, they also the right centric. Xz y. So when we give such structures, it's called bicentric algebra. It's first given by me and my collaborators in the also at the beginning of the century. But later we found, in fact, such structures was already studied by the Greenfield in the last 50s. He gave the name of the association-centric algebras. He used these structures just as the natural generation of the associated algebras. He called the almost the near associated algebras. So these structures, so this appeared independent in the study of the algebra itself in the last 50s. Of course, they have some complete structural theory. Anyway, we can see we gave the notion of the pre-lead. They have the several other names, and we also find that they have several important subclasses appearing in different fields. So this is a brief introduction to the to know from the very simple identity we can get some of the simple results. So next is my outline of my talk, the series talk. Since, as I pointed out, we hope to give an introduction why it really is important. So we should pay attention to the relationship, only relationship with the other structures. So my talk will be divided into 3 parts. The first part is the appearance of 3D. That means I will give more details. The roles being by the pre-lead. Second, we will give some basic properties and construction. The third part, I give you 3D and classical Java. I think this part should be related to the theme of this workshop. The classical equation will have will relate to the variables and they will be related to the composition. So over the conclusion is from 3D we can give some construction of solutions, natural solutions to classical equation. Then it's quite possible to give some derived the condensation structures, the European complex, the European algebras related to such solutions, and even related to the 3D. Okay. So the first I will give some examples why 3D is so interesting. Why 3D appear in some structures. In these structures, we will see why such structures, why we give some of the algebra structures, why the product is left-centric. Okay. Oh. Okay. first we gave you at first we gave you the first one, the affine structure. This is also why the Lundberg introduced the left symmetry structure. This is Lundberg. For given a Lie group, and we give a connection. Okay. For this connection, usually we can define the culture tensor by usually Cxy y x3 minus xy x3x. And in space, usually G is just the algebra of G. Okay. And the solution. Bxy. I think here we need just give a group, but a connection. Usually we needed to ask the G should be the Riemann metric. So just the connection needed to be the Levi-Smith connection. So the most the most simplest example for such structure is we should count flag, local flag. Of course, it's left invariant. Should be left invariant. Local flag means the Cxy torsion free and the torsion is 0 and the torsion is also 0. So it's very simple. Such structure is called the affine structures on V group. Okay. So when we give such structures, natural the question is whether such structure exists. Why? Whether. Okay. So this a problem of Lie integral or Lie group in geometry. So we can transfer to equivalent problem in integral. If we denote xy equals to x dot y, what happens? So you can see the quarter is 0 and the torsion is 0. It's the torsion is 0 and the torsion free. So we will see G is affine structure equals to the G dot is free. So, imply. But if it's free, if the G is just the lifting of the V G is just connect and simply connect the manifold, so it's the equivalent. Right. So in this sense, we can see the affine structure of the group is equivalent to we should study the pre-lead. So here, the counter is 0. The left assembly of the operator in algebra is just have the geometrical implication. Is the counter is 0. Here, and counter is 0, that means the commutator is linear. And here, that's the reply substituted in this one to this one, we get the pre-lead structure. So this means the pre-lead is appeared very naturally. It comes from the last 60s, given by from the geometers. Okay, just from the pre-lead we can construct a natural or fun connection. So this from the geometry. So that's the reason from the last 60s up to the last 80s, the pre-lead is a very active field in the geometry. But later, due to they have not the complete structure theory, not have a good representation theory. Later, we give more explanation. So the study is stopped. They have very few progress since the last 80s. But from the end of the last century, due to it, the pre-lead appeared in the study of the representation theory in the quantum field theory. So it become the re-active again. Anyway, so firstly, it has the many the very good and wrong on geometry. On geometry, it comes from the affine structures. Okay. Second, it's okay. James Harper in the 1963, he used he first gave the notion of the pre-lead. He used the graded pre-lead structures. Okay. Usually they use the right centric, but in order to be consistent, we study we still use the pre-lead, the notion of pre-lead. Here we use the right centric. Give a vector space. We can define the complex. Okay. It's complex. It's very easy. We can define a circle from CP, VV, and CP, and CQ. CP plus Q minus Y is by F to T should be 1. can define sigma I. Oh, okay, we can see the variable is the p plus 1 minus 1, and for the s position, we replace this part by g. Here is the q variable, and the total of the q variable, so it's well defined. And we define x equals to I equals to 1 into p, right, the f e. Okay, it's also well defined. Right. Then conclusion. So we put all of the such structure together. We can define the C dot VV. All of from the sum from the C from the 0 to the infinity. So conclusion is C dot VV is the circle is right. Thank you. So that means for any vector space, by this natural definition, we can define a completion, a product. This is defined on the complex is a right subject by this one. So you can see the structure is very natural, and the structure is also important. Okay, this also depends on any vector space for the infinite dimension. Why is related to the information theory of the social algebras. So we use these structures. Okay. We can see here this complex is one. We should extend by graded version. So we define graded version is x1 fp plus q minus 1 equals to I from 1 to p. We have graded version. Graded version is q minus 1, I minus 1, I minus 1, x minus 1, p minus I plus q minus 1, I plus q. Okay. For this one, this also simplifies the graded version of the left symmetry integral. This xy right minus equals to y3 x3y. Give a graded version. Here is the graded space. Okay. Here we refine V by associated algebra. For the associated algebra, if we want to define a common theory, we need to know the co-boundary operator, right? So that means we should define a dirt. Delta square is 0. And due to this property, we can define the cohomology theory by the cocycle and the coboundary, and the cohomology just the quotient space. So
For this one, we can define the dirt by ith. Okay. It's from CPAA. So we here is the word A. CPAA plus E plus 1 A. Dirt ith equals to mu ith plus mu ith mu. What means mu is A tensor 2A associated product. We can see, as I said, the key point for how to define the copolymer theory of the associated algebras, we should define the copolymer operator. The copolymer operator is come from the right-centrifugal product. The right-centrifugal product is here we can know this from the A tensor A to A, and it's from the A is plus the C2, and here is CP. So the product is CP plus 1, so it's well defined. Here also, it's in the CP plus 1. So from this one, here we use the right-centrifugal product, that's given by this one, and here is the associated product. So we can get this one. And the more important, by this one, we can learn where it's 0. So that's the reason the James Harbour introduced the 3D. First, they define for any vector space, define a natural product in the complex. And then he used these structures to give the graded version. And for the associated group, he can define a natural copolymer operator. Then he get what they need. The copolymer operator specifies the square is 0. So that's the most important, I think, the two examples appeared for the 3D. The first 3D appeared in the fan geometry. It's just to give the flat connection. Here, we also can see the 3D also give the definition of the whole triangle. It's called the whole triangle from the theory of the associated algebras. We use this one to define. Without this circle, I think it's quite difficult to define the copolymer operator. So that's the reason the James Harbour called it the 3D. They also call this the name is the 3D system. I think maybe this time. I think I should have stopped here today. Next time I will give the most of it.
Any quick questions? Yeah, otherwise we thank